Okay, so let's start today's discussion. Hello, uh, good evening. My name is Devadun Banerjee.
So good evening, sir.
So I'm going to start this today's session. Uh, Welcome to the live session of Physical and Electrochemical Characterizations in Chemical Engineering NPTEL course. I'm a PhD PMRF scholar of Indian Institute of Technology, Delhi, and this session is being the fourth live session of this particular NPTEL course. So in this particular live session, we briefly discuss about what has been taught throughout the week, and then also discuss some of the sample problems. Uh, so we will do similar things as well. So in this week, the first lecture was all about the physics option. So physics option basically is used for the surface area and pore analysis, the pore size distribution, and uh, pore volume calculation, and also the surface area calculation. So the content was introduction to physics option, and then classification of the porous materials, different absorption isotopes, and brief computational methods of surface area and pore volume. So if you see of the properties of porous material, so obviously when we talk about the porous material, it means that there will be a distribution of pores. So how this particular distribution can be there? It can be from a very small pores, like which are called micropores, which have the size less than 2 nanometer. Then it can have mesopores with the size of 2 to 50 nanometer, and then it can have macropores, which are having a big size like 50 nanometers. Right. So with this information, this particular information is actually important because we want to know how our surface of our the the physicochemical activity, our particular material would exhibit. Apart from the pore size distribution, like you can also get the pore volume, the surface area. Obviously, the more porous it has, uh, the structure is, the generally it generates more surface area. And as I told, like these are basically a very prominent and important properties for nanomaterials, adsorption, adsorbents, and also catalysis. So, like a porous substrate we can use, which will have a big surface area, a large surface area, upon which some active components, some metals or some other active parts, active compounds, which can be, deposited or impregnated or loaded, which will be taking part your chemical reaction or some other things like that. So it is obviously advantageous to have higher surface area for higher reactivity. Higher surface area leads to higher performance or activity, as told. The formation of pores is usually initiated during the preparation process, especially with the operations such as drying, calcination of catalyst material. So when you are having the synthesis of the catalyst material, so you go through basically initially in normal either impregnation method or co-precipitation method or sol gel process. There are multiple processes. So after that you will be drying your material. So excess solvents and all those things will be just evaporated. So during this drying, what will happen is the active component will get gradually loaded onto your main item. the substrate, the high surface area substrate. This particular pore enhancement is occurs, and then you calcine your material at high temperature, 500, 600, 700. This kind of high temperature calcination is done. So during this calcination under air, what happens is usually like the oxides are actually formed. Especially if you talk about the catalysis, the metal oxides are generally formed during the calcination step. And during this, apart from this kind of chemical process, the metal oxides from some metal salts, usually you'll be using the metal salt, metal nitrate or chloride or something. So it will be converted into oxide. So this is a chemical process. So apart from that, there will be obviously some physical changes also in your material, in your precursor material, whatever originally you have put. So that particular physical process is accompanied by some particular pore structure development, some kind of crystal structure development with some maybe ordered pores or uh, some mesopores like that. Okay, so this kind of pore size distribution and the number of pores determines the internal surface area. Pores being small, it hinders the entry of incoming molecules, which does not allow it to enter the inner part, and hence the catalyst will be less reactive. So as I told, like more porous means more surface area. So it means that if you have a microporous material, so it will the pore size will be less than 2 nanometer. It might have a very high surface area due to the microporous because a lot of small this kind of pores will be there. But if your molecule, reactant molecule, is having a size greater than 2 nanometer, greater than the pore size, whatever pore size you have, then what will be happen? Even though you are depositing some metals or some active component on this pore walls, or inside of that particular pores, those will be basically underutilized. Those will things will not be utilized for your desired reaction. So that is the thing. The pores being small, it will be hindering the entry of the incoming molecule, which does not allow it to enter the inner part. Okay, hence, the catalyst will be less reactive. So ultimately, it will be of no use. So that particular thing is important to be optimized through the catalyst preparation procedure, or your nanomaterial synthesis procedure. Scientific community interested in the pore structure, and attempts are being made to optimize these from the preparation, precursor, and manufacturing conditions to provide maximum utilization. That's the thing I told. So adsorption basically takes place on the surfaces which are solid for balancing and the forces on the solid surface. An attractive force is created for the incoming adsorbate molecules so as to initiate a reaction or a process. Van der Waals attraction forces develop which are due to the shape and size of the incoming molecules. So if we give it with a certain particular pressure or certain energy, so they will be when this particular distance is getting decreased between the adsorbent and adsorbent, there will be a certain attraction force will be there, such certain kind of affinity will be there, which is usually called as a physical thing, the van der Waals attraction force. It will be varied depending on the shape and size of the incoming molecule, as well as obviously the your adsorbent material also. So if we talk about the entire adsorption process, the adsorption process can be classified into two types depending on the type of interaction with the adsorbent. Physisorption, where basically, and another one is chemisorption. So basic difference is physisorption, as by the name, it forms some and binds by some physical forces such as van der Waals force. Uh, and in chemisorption, there will be some chemical bond that will be formed. So based on that, there will be some chemical changes. Okay. So if we talk about the basic differences between the physics option and chemistry option, see, so for physics option, the enthalpy changes are small. So very small changes will be there because it is not a very strong adsorption. Okay, this is a very easily reversible thing. So therefore, the enthalpy changes are small, only 10 to 40 kilojoule per mole. Whereas for chemistry option, because of the chemical bond formation is there, a kind of a stronger interaction is there. The enthalpy change is also quite large, about 100 to 400 kilojoule per mole. Physics option decreases with increasing temperature and it increases with increasing pressure. Whereas chemistry option usually takes place as at the higher temperature conditions. Okay. In physics option, there is a possibility that a multi-layer adsorption occurs. So first, the monolayer adsorption will be occurring, and then after that, once the monolayer adsorption is done, based on your adsorbent uh, type, there can be some multi-layer adsorption take place. But in chemistry option, it usually basically a monolayer formation. Okay. Uh, as I told, physics option is a highly reversible thing. Just withdraw the pressure, withdraw the energy which you are giving in terms of pressure or other energy force. It just gets reversible. But chemistry option is a kind of a mostly irreversible because there is a chemical change which often is a permanent change. Right. So physics option is used to determine the total surface area, pore volume, pore size distribution of the adsorbents, and for various catalysts. Chemistry option is used to estimate the area of catalytically active sites and the dispersion. So then if we talk about the adsorption isotherms, these are very, very important because this will give you, characterizing your material qualitatively as well as quantitatively. So adsorbate molecules in the gas phase are distributed in equilibrium between the adsorbent surface and the liquid phase when they come into contact with the adsorbent surface. The factors basically this kind of distribution of the adsorbate molecules, okay, on the adsorbent, this particular distribution, the factors are pressure, temperature, nature of adsorbent, and obviously nature and pore size of the adsorbent. Okay, so typically based on the IUPAC nomenclature, there are usually 5 to 6 types of isotherms are there. Here on 5 types are shown. So type 1, type 2, type 3, type 4, and type 5. So type 1 adsorption isotherm is basically for the materials having the small pores or a microporous structure. Okay, you see there is a up to a certain pressure, there is the adsorption happening. After that, uh, even if we are increasing the pressure, there is not um, a considerable change is happening in terms of the adsorption. Okay, so this type of materials are usually microporous in nature. Clear? Yeah. Now type 2 and type 4, if you see, there are basically observed for the adsorbents that are not porous or having a monolayer multilayer uh, adsorption. Okay, unimpeded monolayer multilayer adsorption. So basically what is happening is up to this particular point, up to this initial stage, if you see this initial stage, there is a similar like type 1 isotherm. There is one layer of adsorption in there. Then after a certain pressure value, if you increase the pressure value beyond this particular certain point, there is again a quick increase of the adsorption volume. Okay, so that is a thing is written here at low relative pressure. The adsorption volume initially rises quickly, and then once the monolayer creation of the adsorption molecule is complete, the multilayer formation starts. Up to that, it is the monolayer volume that is shown here. Is it can call it as a VM. So is there is a sharp knee uh, of this particular adsorption isotope. Okay. When the relative pressure approaches unity, close to unity, this relative pressure P by P naught, sudden rise signals bulk condensation of the adsorbed gas into liquid. Okay, because of the very high pressure, what happens is some of the gas molecules which are being adsorbed on the adsorbent, they start to condense, and because of that, there is a sudden rise of the uh, this adsorption volume. If you, on the other hand, if you see the type 3 and type 4, there is not a significant this kind of knee kind of shape is there, right? So which indicates that there is a certain interaction within the adsorbate molecules themselves. Okay, so the adsorbate interactions are actually stronger than the adsorbate adsorbent interaction between, like nitrogen is being adsorbed onto your catalyst. So compared to this particular nitrogen catalyst interaction, the N interactions is much more prevalent in this kind of materials. So obviously these would be again dependent on the type of material you are using. So now after the adsorption, there is a point when you're withdrawing your pressure. So as told that physisorption is basically a kind of reversible in nature. So if you withdraw the basically the energy, so we are giving your energy in terms of the pressure. So if you withdraw the pressure, what will be happening is that the material, the adsorbate will be getting dissolved. So the desorption curve generally follows the adsorption curve. It will be the similar in nature, but it sometimes what happens is for mesoporous and macroporous materials, it causes a wide loop. So it does not exactly retraces the path of the adsorption curve. Rather, there is a slight difference between the adsorption and the desorption paths. Okay? This is called the hysteresis loop. And why it occurs? It occurs because of the capillary condensation in a multi-layer and pore filling regime. So in case of mesoporous and macroporous, where the larger pores are there, there is a always a better chance that some of the gas molecules are getting condensed inside the pores at the higher pressure. So therefore, some of the molecules are getting condensed and they get into the liquid phase. As a result, the pressure would get varied, the vapor pressure would get varied, and automatically the adsorbed volume would obviously get changed. So because of that, it does not sometimes get exactly matches with the adsorption line. So the type A of hysteresis loop is attributed to the cylindrical or tubular type of pore and narrow distribution of uniform pores. The type B resembles the intricate structure of pores with linked networks, or these are basically called a ink bottle type of pores. So if you just check in the internet, then you'll get the exact shapes of your pores based on the hysteresis types. Type C, it indicates the pores with some capillaries having a large diameter, more than 500 angstrom, and the type D is having a slit-shaped pores, uh, but in the pores will be basically in the microporous region. So as we are talking about the isotherms, now there are several types of isotherms. Different groups of scientists have proposed different isotherms. which can actually like correctly model things, your pore structure, your adsorption volume, and all these things. So Langmuir, Freundlich, Temkin, BET, these are the different types of isotherms, and every types of isotherm has some assumptions. And obviously, it has some assumption. It means that it has some this kind of drawbacks or challenges. So you need to check those things. Uh, so, for example, the Langmuir isotherm have the absorption such that the surface is homogeneous in terms of energy, whereas in reality it never happens. There is no contact between the adsorbed molecules that are adjacent. Again, in reality, there is some adsorbed interactions. Adsorption is often limited to fewer than one full monolayer coverage. All adsorptions follow similar process and culminate in the formation of the same adsorbed structure. And Langmuir isotherm is basically for the type 1 uh, that we showed earlier, the type 1 kind of isotherm where monolayer adsorption is occurring for a microporous material that is good, well modeled by the Langmuir isotherm. Okay, so it's very much true for the coverage smaller than that of a monolayer, even for a smaller than that of a monolayer, it holds true. Uh, when going for further complicated things for a monolayer or even greater absorptions greater than monolayer like multilayer absorption, then things getting deviate. Similar to Langmuir isotherm, the BET isotherm, so these are named in some eminent scientists, Bronner, uh, Emmett, and Taylor. So this particular BET is particularly important, and we use it for the surface area calculation. So the correlation between the volume adsorbed at a given partial pressure and the volume adsorbed at a monolayer coverage. This is particularly given by this kind of expression where if you take the P by P naught as x, then you will be getting this x by V into 1 minus x equals to 1 by Vm into C plus C minus 1 by Vm into C into x. This is the kind of a equation we'll be getting where uh, clearly you see the C minus 1 by Vm into C is the slope and the intercept will be the 1 by Vm into C. Vm is basically the monolayer absorption volume. Okay. So basically this kind of C, if you can get the value of C, this particular C signifies the adsorbed surface interaction. So the higher the C value, it usually corresponds to a higher interaction. Similarly, from this kind of equation, if you solve them, then you can get the monolayer adsorption volume simply by 1 by slope plus intercept, where this is the slope and this is the intercept. So this kind of small calculations you can use. In reality, we have the softwares which do it for us, but this is the uh, you know background of this particular calculation. Okay. So these are the first question today comes. Which of the following effect can result in a transition from physisorption to chemisorption phenomena? Decrease in temperature, increase in temperature, decrease in pressure, increase in surface area.
B. Increase in temperature.
So yeah, the correct answer is the increasing temperature as told earlier. Only similar and just if we increase the temperature, basically what will be happening? The physics of the molecule should get dissolved because it's a very weak force, a van der Waals force. On the other hand, what will be happening? There will be some chemical changes or chemical reactions will be occurring, and that will call as a chemisorption, chemical adsorption. And some chemical bond formation will be there. Which of the following statements is not true with respect to chemisorption? Depends on nature of adsorbate and adsorbent, has a large heat of adsorption, forms a unimolecular layer, and it occurs at a low temperature.
Option D occurs at low temperature.
The correct answer is it occurs at the low temperature. Obviously, it's not true. Just we discussed it, this particular thing. It's true for the physics option, not for the chemical option. So, which of the following is an assumption for the BET theory? The solid surface possesses uniform localized sites. The adsorption at one site does not affect adsorption at neighboring site. Physical adsorption of adsorbate occurs, resulting in the formation of multilayers, or all of these. So basically, the assumptions are similar as the Langmuir isotherm theory. So all of these particular assumptions hold true for the BET theory as well. The solid surface possesses uniform localized sites. The adsorption at one site doesn't affect adsorption at neighboring site. Desorption of adsorbate occurs, resulting in the formation of multi-layers. Okay, just this particular assumption is a little bit different from the language. Other than rest of them are similar. Which of the following statements is correct? Chemisorption is stronger than physisorption. physisorption is stronger than chemisorption, they're both equal or they cannot be compared.
Answer is A, sir.
So yeah, the correct answer is chemisorption is a stronger version than the physisorption simply because there is a permanent kind of chemical bond formation is there instead of just acting based on some physical forces, right, in physisorption. So these are the figures of the types of isotherm. So for the type 1, what is the correct option? Multilayer formation. It is applicable to mesoporous adsorbents, monolayer adsorption, or bulk condensation.
C, monolayer absorption. I think C, monolayer absorption.
Yeah. So correct. So monolayer adsorption is basically the type 1. I've discussed this particular thing. So this is basically related to the microporous material. So beyond increasing your pressure beyond this particular VM or monolayer volume, there is not enough increase of the adsorption volume. So basically this is applicable to the monolayer adsorption, not the multilayer, and is applicable for the microporous, not for the mesoporous, because obviously there will be mesoporous, there will be a chance of the bulk condensation is there, there will be chance of multilayer adsorption. So in one way or the other, it's correct that it's a monolayer adsorption and microporous materials. Now, the type 2 and 4, what does it represent? This particular sharp knee, the extent of multilayer adsorption, transition from mono to multilayer adsorption, the decrease of the adsorption volume at low pressure, or none of these.
I think A, extent of multi-layer absorption. Absorption. Oh, sorry. I think B, transition from mono to multi-layer absorption.
Yeah. So the B option is correct. It's basically the transition from mono to multilayer adsorption, represented by this particular knee thing. Up to this particular knee, there is a monolayer adsorption, and beyond that, when there again a increase of this particular uh, gas adsorption volume, there is a, we call it as like a multilayer formation gets started. The BET theory is used in calculating the surface area of adsorbent, surface area of adsorbent, surface area of adsorbent and catalyst. None of these. So the correct answer is surface area of adsorbents and catalysts. So if you have going for some adsorption uh, application, or if you're going for some catalysis applications, both for both these things, this particular BET theory is important to calculate the surface area. The volume versus thickness plot attains a straight line going through the origin for which type of material? Mesoporous, microporous, non-porous, or none of these?
Option C, non-porous.
Yeah. So C, non-porous is the correct answer. So basically, uh, the T-plot technique. This is the question from a particular technique which is called the T-plot technique, where the micropore and macropore size distributions, volume, area, these are actually can be these information we can get, uh, and it can be got from the nitrogen adsorption starting at a low relative pressure, P by P naught less than 10 to the power minus 5. Okay. So comparison of a microporous materials isotherm to a non-porous materials typical type 2 isotherm. So as already earlier told, that type 2 and type 4 isotherms are usually often called for some non-porous kind of materials. So if you get a reference from those non-porous materials, and then if we compare our particular microporous materials isotherm, then we can get this particular information. So the volume of nitrogen adsorbed versus the statistical thickness of an adsorbed layer on a non-porous reference. So at a particular corresponding relative pressure, if we take this particular data, how much volume is adsorbed and how much basically statistical thickness is of the adsorbed layer is there. This particular data if we can obtain, and then compare it with our particular material. Then it uses we can actually get our information. It uses the measurement of BET surface area through which the micropore surface area can be indirectly measured. So the calculation method consists of experimentally obtained isotherm redrawn as a T-plot. So the plot of nitrogen gas adsorbed corresponding to the statistical thickness of an adsorbed layer. How much that particular gas adsorbed, it will be corresponding to the statistical thickness. How it will be corresponding to the statistical thickness? For that, there is this particular number of equations. Uh, the Harkin-Jura equation or Halsey equation, or even in particularly there has been also another model like for carbon-based adsorbents. This particular model can be used like for give the p by p naught value, you get the statistical thickness, and for each statistical thickness, you get certain volume adsorbed volume. So just p by p naught value, you are changing to the statistical thickness value. So if we plot that and the volume versus thickness plot for a non-porous material, if it is a non-porous material, it will be passing through a straight line going through origin. Okay. If it is a microporous material, there will be obviously a straight line, but it will not pass through the origin. And the size of the y-axis intercept, this particular intercept, if you calculate, it will be giving you the micropore volume. Okay. Similarly, for a mesoporous and micro and mesoporous, there will be no entirely not an straight line. There will be this kind of hinge will be there. So the T plot will be deviating from a straight line at a higher thickness value of the adsorbed layer. Okay. So just discussed, the T plot does not pass through the origin, and the size of the y-axis intercept gives the micropore volume for which kind of materials: mesoporous, microporous, non-porous, or none of these. So just discussed, not giving time on for this. So it's always obviously the microporous material. For microporous materials, the P versus V curve will not pass through the origin, and the micropore volume we can get from the y-axis intercept. Okay. Now coming to the lecture 2, which briefly discussed about the physics option measurements. Uh, so basically, the latter part of this particular lecture 2 is for basically the instrumentation, which you can check from the lecture. Not going too much detail about it. Basic concepts I have already discussed of the physics option. Apart from that, some bit discussion is there. Physics option. Let us see that. So basically, some micropore volume method, which I told that the volume thickness curve obtained from the experimental data is compared with a standard reference for non-porous material. The y-axis intercept value is transformed from the volume of a gas to that of a liquid, yielding the micropore volume. Okay. The equation used for the micropore volume is given by this is the equation, the intercept divided by 22.4 into 10 to the minus 3 multiplied by 34.6. 34.6 is basically the molar volume of liquid nitrogen. Liquid in that particular nitrogen is basically used as the adsorbate molecule. So based on that, you can get the micropore volume. The micropore surface area you can also get if the volume adsorbed is represented as the volume of the associated liquid. Then you can basically get the T will be basically the thickness will be basically the liquid volume divided by total surface area, right? So if we get from this, what we'll be getting that if you can basically plot the V liquid, the adsorbed liquid volume and the thickness, so it will be giving the slope of this particular plot will be giving the T plot surface area. So the T plot surface area basically will be giving you the meso or macroporous surface area, and if you just subtract this particular mesoporous surface area from the BET surface area, you'll be getting your micropore surface area. So in this way, you can obtain these particular informations. Okay, you can check this particular lecture for further detailed discussion. And another interesting thing is the Kelvin equation. So Kelvin equation is basically used for the pore size distribution analysis. Uh, this uses the temperature dependency of the vapor pressure to obtain the pore size distribution. So how it obtain the pore size distribution? Basically, it works on this kind of equation where ln p by p naught equals to minus 2 gamma v liquid cos theta divided by small r in multiplied by capital R. Okay, if you see here that the these particular values like v liquid cos theta capital R capital T, these will be basically constant depending upon whatever is like conditions you are using your experiment. The surface tension gamma, these are basically constant values. Basically, you will be varying the pressure, and accordingly, this particular small r will be changing depending upon what temperature you are operating. So small r is basically the pore radius. So basically, you will be changing the pressure. So accordingly, the depending on how the amount of adsorbed volume, the you'll be getting the indirectly you'll be getting the pore radius. Okay. So if the capillary radius is small enough for the given liquid, the pressure at which the condensation or evaporation occurs within the pores will be the less than the free surface vapor pressure. So there is obviously a whatever thing you are getting, making adsorbed nitrogen, for example. So there is a without any constraint, there is a certain free surface vapor pressure is there for maybe nitrogen, right? So, but in this kind of condition, that particular vapor pressure, when it is getting absorbed into this porous structure, into these pores, that particular vapor pressure will be different. So, if that particular capillary radius for the given liquid, whatever thing is getting condensed, uh, it is small enough for the particular given liquid, that pressure will be the less than the actual like without any constraint wala jo vapor pressure hai, that will be the less than that. Okay, so P1, if we consider it as a P1, that P1 will be less than uh, P0. Okay, P0 being the uh, free vapor pressure. Similarly, there will be, if there is a further condensation of that particular adsorbate occurring, then the bulk condensation occurring, then there will be a certain again an increase of the pressure. So that if you consider it as a P2, so P2 will be greater than P1, what was earlier, but still the P2 will be less than P0. So as the equation shows, as I already told, that depending on the radius, the condensation can start before the reduced pressure is equal to unity. Okay. So in just simple way, just if you just increasing the pressure, you'll be getting some adsorbed volume. By that equation, if you just put the pressure value, you will be getting some R value, small r value. So based on that, at different pressures, you'll be getting different small r values. Based on that, you will be getting that a kind of distribution of that pore size or small r's in simple words. And how this particular pressure can be varied? It can be varied by variation in the temperature. Okay. So the vapor pressure is basically changed through the temperature to measure the volume adsorbed and the solve of the radius, which I just told. Okay, and you'll be getting the pore size distribution. So for pore size distribution, there is the Barrett, Joyner, Helenda, BJH method is the most used method, and again it is bound by some assumptions, such as the condensation occurs in the pores when a critical relative pressure is reached corresponding to the Kelvin radius. Okay, when evaporation or condensation occurs, a multi-layer of adsorbed film exists on the pore wall. So this is, if you see that this particular is a pore, so there will be a certain film on the pore wall. So yeah, we are considering that thing also in for this kind of pore size distribution calculation. This particular film has same depth or thickness as the adsorbed film on a non-porous surface. The actual pore volume evaporation is composed of the volume evaporated out of the center core plus the volume dissolved. So both of these particular volume will be taking for the pore volume calculations. So the film as well as the center core. Okay. So the mesoporous materials are having a pore size in the range of 2 to 50, less than 2, greater than 50. Yeah. So the correct answer is 2 to 50 mesoporous, less than 2 is the microporous materials, and greater than 50 nanometer is the macroporous materials. Just a simple question. Which of the following forces is involved in this option? Magnetic force, van der Waals force, electromagnetic force, gravitational force.
B. Van der Waals force.
So that is basically from the physics option part, and a little bit brief discussion from the chemis option thing. So basically, as for the chemis option, when the gas molecules impinge on a surface, they transfer their momentum and give rise to a pressure on the surface. Okay. Some of the molecules may stick on the surface and may be weakly bonded to the surface by van der Waals forces. This is basically the phase option thing. And if the interaction is stronger, if there is a particular chemical reaction or chemical bond formation or dissociation occurring, and by that there is a adsorption occurring, it is called the chemisoption. During chemisoption, the entities of the molecule may break up, which is called as the dissociative adsorption. So in particularly, the chemisoption is in particularly important for the metal metal based materials. So what will be important to exploit the reactivity of noble metal surface atoms. So for this kind of surface reactions or maybe for catalytic reactions, it is important to uh, let the surface atoms participate in the chemical reaction. However, for noble metals, they are actually reactive, but they are very much selective in nature. They are very much stable in nature, but the main thing for the noble metals is they are often are very much inert also. So that for that reason we need to exploit a certain high degree of reactivity out of the noble metal surface atoms. So how we can exploit? We have to let them react with small molecules. So whatever adsorbate is there, hydrogen or oxygen or carbon monoxide like that. Okay. Uh, Once they uh, just the gas passing is done, you have to count the number of molecules that have reacted. So basically, if you have a particular detector, it will be giving you that particular measurement, that how much quantity of you know hydrogen or oxygen that is getting reacted with the particular surface. So based on that, we can actually obtain the how much noble metal atoms are participating in the reaction. So will be can you obviously will know the stoichiometry of the reaction which is happening. So maybe for example, copper laser cupric oxide. So cupric oxide plus hydrogen if you give, maybe there will be a reduction in copper and there will be a H2O formation. So in the detector will be telling that there is a certain amount of hydrogen is getting passed for a certain time and then there is a decrease of hydrogen signal by this amount. So we'll be taking that okay, this amount of hydrogen is actually getting reacted with our metal oxide surface, and we know the reaction that cupric oxide plus hydrogen gives copper plus H2O. So we know the stoichiometry, and based on that, we'll be getting that okay, based on the stoichiometry, taking it as a absolutely uh, ideal reaction. So maybe x moles of hydrogen is getting reacted. So there is actually x moles of surface cupric oxide atoms are there. So based on that, and there is stoichiometry. There is of x moles of copper, metallic copper is getting formed. So based on that, you correlate with your catalytic reaction. So what kind of probe molecule you have to choose? It might be selective for the reaction with metal when compared to its support. So when give, for example, the example I've given just the hydrogen you are giving. So the cupric oxide maybe it's put on a certain support, maybe silica or alumina or some other maybe. I don't know. So based on the relative affinity, you have to see that that hydrogen should not react with the support, rather it should react with the metal primarily. So it must be selective for that. Again, it must be selective for reaction with surface atoms, not with bulk. So usually the reactions happens with the surface atoms only initially, and then if you give a high pressure or high flow rate for a high temperature a longer time, then there's a bulk changes is there, and the reaction must be irreversible. So it again for the stability point of view, if you're going for Chemist option, that particular reaction must be irreversible. Otherwise, you will be not able to defend your case. Like when just if again the copper is getting self oxidized to the cupric oxide and giving back the hydrogen, then that particular calculation might be wrong. Okay, so there is a certain activation energy required for the Chemist option. So before the molecules become firmly attached to a surface, they must overcome an energy barrier. So that particular energy we are giving in the form of temperature or pressure like that. Okay? So the adsorbed molecule, it might undergo dissociation, which is called as a dissociative adsorption. What is the dissociative adsorption? The adsorption accompanied by a dissociation, having one or more of which is attached to the adsorbent surface. So basically, again for the hydrogen molecule. So hydrogen molecule when it is getting adsorbed on the metal surface, it might not adsorb directly as a H, H2 molecule. It might get dissociated in between, and like hydrogen radicals would actually get adsorbed on the catalyst surface. Okay, so that is usually called as a dissociative adsorption. So if you see, like this particular for molecular hydrogen, which is example also given, the iodine monochloride on aluminum, or oxygen on silver. So this kind of uh, examples are there where dissociative adsorption takes place. So especially where dissociative adsorption of hydrogen takes place, especially on the metals in their inactive state. And this particular kind of dissociation is called usually the homolytic. So basically the two fragments which it is creating like this. So these are equivalent. It is called the homolytic cleavage. On the other hand, there can be a heterolytic cleavage also occurring, where when the dissociation actually splits asymmetrically. Okay, so when this particular heterolytic cleavage occurring, usually for a three center adsorption. For example, water adsorption, because there is H2O, so there is a three center adsorption modes. So often it occurs that OH it goes to one part and another H as a free radical it goes adsorbed as a different entity. So like that H2S, methane. So for more than two centers, it is usually very common, the heterolytic cleavage. Even nowadays actually the for hydrogen adsorption also nowadays various papers are there, recent papers, you can check those. There is actually a heterolytic adsorption or heterolytic cleavage is also getting very much popular. People are suggesting that actually heterolytic cleavage is also very much helpful for certain reactions or like that. Okay. With this, just last question of the day. Enthalpy change associated to chemisorption process generally lies
B.
within.
B. 100 to 400.
Yeah. So 100 to 400 kilojoule per mole. Basically, the enthalpy change for chemisorption is actually higher compared to the physisorption, and it lies in between 100 to 400 kilojoule per mole for chemisorption. Okay, so that's all from my side today. Thank you for joining.
Thank you, sir.
Thank you, sir.